Hi everyone. Okay, we are finally almost done with step 5, proving the multiplication axioms for the fields for the Dedekind cuts. What we have left, we're getting so close, but as I said several times, it got harder and harder and harder as we went, and we're up to M5, which is multiplicative inverse. Which means that there exists a beta for any alpha such that alpha beta equals 1. First thing, so we're showing that this exists no matter what alpha is. Just to define beta again, beta consists of all elements p such that 1 over p times 1 over x is not an element of alpha. So the first thing we had to do was prove that this is a cut, which we did. And then we have to prove that these two sets are equal. And we do that by proving inclusion in both ways. First, that alpha beta is a subset of 1, and then that 1 is a subset of alpha beta. We've already shown this one, so we're down to this. And in last video, we looked at Landau's proof instead of Rudin's proof. We had it mostly figured out, so all I'm going to do in this video is, now that we understand Landau's proof, I'm just going to write it down neatly and completely so that we can follow it more simply. His theorem where he proved this statement was Theorem 152, but in order to do that, he had to use an earlier theorem he had proved, which was his Theorem 132. So I'm just going to call this lemma 132, just for the heck of it. So the lemma is that given any rational number x greater than 0, so positive, and given a cut alpha, then there exists a p that's an element of alpha and an r that is not an element of alpha, such that r minus p equals x. Minus is the difference between two numbers. It's the distance between two numbers. So what this is saying is that for any number, there's going to be two numbers, one inside of alpha, one outside of alpha, that are x apart. So we're starting with x. So whatever this distance is, we'll be able to find one number that's inside of alpha and another number that's outside of alpha, that the distance between them is x, okay? That's what we're trying to do. So let's move to the next page to prove this. Proof. So first I'm just going to point out that x must be positive because if p is an element of alpha and r is not an element of alpha, that means that on the number line, r is going to have to be bigger than p. This is our result A. Whoops, p has to be less than r. That means that r minus p is always going to be bigger than 0. So let's start just with an arbitrary number inside alpha. Call it p1. So let p1 be an element of alpha, and consider all rational numbers of the form p1 plus nx, where n is, of course, an integer. Where n is an integer. Okay, so the first thing just to recognize is that not all of these numbers will be in alpha, will be elements of alpha. Because if Q is not an element of alpha, then Q has to be greater than P1. That is just again, if P1 is in alpha and Q is not in alpha, then Q has to be bigger than P1. So if that's the case, then by the Archimedean property, there is a suitable n such that nx is greater than q minus p1, right? Just take this as y. We have x, so there's going to be some n that makes nx bigger than the difference between these two. Okay? So if we start with that, is greater than q minus p1, then we add p1 to both sides. We have p1 plus nx is greater than q minus p1 plus p1. And then these cancel. And we have that p1 plus nx is greater than q. And that means that p1 plus nx is also not in alpha. This is b, because if we have alpha here, p1 is here, q is here somewhere, and if we know that p1 plus nx is even bigger, then it also has to be outside of alpha. What we're saying here is that there's some nx that is bigger than the distance between these two, right? Because when we added p1 to this one, we got past q. So this is just bigger than this distance. Okay, so the next point is that the set of all of the n's such that p1 plus nx is not in alpha contains a smallest element. And this was something that we proved when we were looking at the Archimedean property, because we had to prove, if you remember, we were looking at the well-ordering principle of natural numbers, and that the natural numbers, any set of natural numbers always has a least element, and so any set of integers that's bounded from below has to have a smallest element as well. Okay, so we'll call this u. Okay. Okay. So what do we know so far? We have that p is an element of alpha, and r. Oh no, I'm sorry. Wait, that's not what we have. What we started with is we started with some element of x greater than 0, and we're looking for a p that's inside alpha and an r that's outside alpha. Okay, that are, and where these two numbers are a distance of x apart. And we chose p1 arbitrarily is in alpha. And what we just did is we said that p1 plus ux is outside of alpha. The u is the smallest integer that puts p1 plus ux outside of alpha. So now we just have to look at these, and we'll be able to, and the result should pop out. So first we'll look at if u equals 1, then set p equals p1 and r equals p1 plus x. So basically we have that p1 is inside alpha, so we're just going to make p that number. And then if u is 1, then we know that this number is outside because it's p1 plus 1 times x. So these are clearly going to be x apart, right? So I'll just show that. So r equals p1 plus x, and then subtract p from both sides. And p1 is the same as p, so I'm just going to change this to p. Right? Because p equals p1. So I can rewrite this as that. These cancel, and we have that r minus p equals x. Okay? So that was easy. So if u equals 1 is easy. Now, if u is greater than 1, and again, it can't be less than 1 because we started with that x is positive. So the n here is going to be, when we have nx, the n has to be positive too because the x is positive. So we have to go to the right from p1. So if u is greater than 1, then set p equals p plus u minus 1 x, and r equals p1 plus ux. Okay? Now, what we're doing here, this is very similar to what we did with the addition axioms, where we had a cut, and we had some p, and we had and we were looking at w, right? And then we established that there was some nw that was just inside of alpha, such that n plus 1w was just outside of alpha. So we've done the same thing here. We minused instead of plussed. But so there's some number that's just outside of alpha. And then if you subtract 1 from it, it's going to be just inside of alpha. So it's very similar to what we were doing before. So with that in hand, we have r minus p equals, just plug these in, p1 plus u x, that's r, minus p1 plus, I'm just going to distribute this out. So it's ux plus ux minus x. Okay? And then we rearrange them. And so it's p1 minus p1, and then plus ux minus ux plus x. These cancel, and once again, we have that r minus p equals x. So that's all we needed to know, because u is either going to be 1 or something bigger than 1. And we show that no matter if u is 1, then r minus p is x. And if p is anything bigger, if u is anything bigger than 1, then we can find an r and a p such that r minus p is x. That's the proof of lemma 132. Now, using this, we're going to be able to prove finally that every positive cut has a multiplicative inverse. This is what we've been working on for several weeks now, and here we go. So as I said at the beginning, we've already shown that alpha beta is a subset of 1. We've done that. So what we have to do now, last thing, is to show that 1 is a subset of alpha beta. So again, beta is the set of all p such that 1 over p times 1 over x is not an element of alpha for some x greater than 1. Okay? In other words, it's all the p's such that the reciprocal of p is a little bit bigger than the edge of alpha. If this is alpha, then the reciprocal of p is going to be at least a little bit outside, so that if x is greater than 1, then 1 over x is some amount smaller than 1, which means that if this is 1 over p, then 1 over p times 1 over x, there's going to exist some x such that we can fit another one in here, so that there's no smallest element here. And that's just because beta, as a cut, has no largest element. So beta's over here somewhere, and as the elements get closer and closer to the edge of beta, there's always going to be one bigger here, which means there's always going to be one smaller here. That's all we're saying with this definition. Okay, so we just have to choose an element of 1 arbitrarily. So choose a v that is positive but less than 1. So it's an element of 1. Now we have to show that this v, no matter what it is, we're going to construct it in a way that it will be also an element. We're going to show that it's also an element of alpha beta. So choose any r inside alpha with r greater than 0. Then by the lemma we just did, there exists an S that's inside alpha and a T that's, outside alpha, such that T minus S equals 1 minus V times R. R is our arbitrary element in alpha, and T is outside of alpha and S is inside of alpha, and this is the lemma. Just remember that, think of this as one number here. So now all we have to do is sum algebra. So we know that R is less than T because R is in alpha and T is not in alpha, and that is property A. So T minus S is less than 1 minus V times T. So we said that T minus S equals 1 minus V times R. We just showed that R is less than T, so that means that T minus S has to be less than this because R is less than T. So now add Vt to both sides. We have T minus S plus Vt is less than, I'm just going to distribute this, T minus Vt plus Vt. Cancel these, and we have that T minus S plus Vt is less than T. Now, if I add and subtract an S to this side, and then you can just put the parentheses around this, so we have that T minus S plus Vt is less than T minus S, is less than, T minus S plus S. Now we can cancel the TS's, and we have that Vt is less than S. Okay? Remember this because we're going to use this again in a second. Vt is less than S. Vt is less than S. That's what we just showed. Now, we also have that T equals 1 over V times T, right? That's just the inverse property. That means that T equals 1 over V times Vt, and that means that T is less than 1 over V times S, because Vt is less than S, then this has to be less than this. So T is less than 1 over V times S, which means, just to rewrite it, T is less than S over V. So that means that, therefore, S over V is not an element of alpha, because we started with T is not an element of alpha, and if S over V is bigger, then it's also not an alpha. That is B. Now let's do some more. V times S over V equals S. V times S over V times the reciprocal of this, which I'm going to write in a strange way, but 1 over S over V equals S times 1 over S over V. Okay, now this, if the reciprocal of S over V is V over S, okay, but it's also 1 over S over V. That is just a weird way of writing V over S. Then we cancel these, and then we have that V equals S times 1 over S over V. Wow, you see where we're going? I think we're close. This is inside 1, this is inside alpha. The only question remaining is whether 1 over S over V an element of beta. That's all we have to prove. Okay, so first I'm just going to show you that it's true, and then I'll prove it using algebra. But if 1 over S over V is in beta, then that means that for alpha here, if 1 over S over V is over here, then the reciprocal of that is S over V, and then there's going to be something here that we can make it a little bit smaller with some x greater than 1, such that S over V times 1 over x is still outside of alpha. So we need to show that there exists an x greater than 1 such that that's true. Now, first of all, I just want to show you that we know it's true because t is not in alpha and s divided by v is bigger than it. So we know that there's going to be, we know that this isn't the smallest element outside of alpha. That shows us that this is in beta. But I'll just do the algebra to prove it. So if we start with that t is less than s divided by v, then if we move t to the other side, we have that 1 is less than s over v divided by t, right? We divided both sides by t. So let x equal that. So x is greater than 1, which is what we want. That means that 1 over x equals t over s over v. And since x is greater than 1, then 1 over x is less than 1. And s over v, which remember is the reciprocal of 1 over s over v. S over v times 1 over x equals s over v times this one, t, over s over v. And then if we just multiply through, we have that st equals vs over v. These two cancel, and we have st over s. Those two cancel, and we have t. So this equals t, which we know is outside of alpha. Therefore, s over v times 1 over x is outside of alpha. Therefore, 1 over s over v is an element of beta. Do you believe it? That's all we need. So we already showed that v equals s times 1 over s divided by v. This v is an element of 1. S is an element of alpha. This is an element of beta. Therefore, this is an element of alpha beta. And that means if this element was arbitrary, if any element of 1 is therefore an element of alpha beta, then that's what we needed to prove. Therefore, 1 is a subset of alpha beta. That's 2, and we're done. Took us a long time to get there because Rudin drastically misled us, but that is it. So we've proven now the multiplicative inverse, and we're all done with step 5. So I just wanted to say a little bit about this before we go. The really interesting thing here is that Landau managed to prove this without using division at all. Rudin has it's becoming clear how he likes to think about things. He likes doing arithmetic. So if he has two numbers here, this is alpha and this is r, and he wants to get halfway between them, he thinks in terms of literally just add them together and divide by 2. That worked fine for addition, and I still think that he didn't check. This doesn't work for multiplication because with multiplication we have to deal with square roots, not division. So I don't think this works. And it's interesting that Landau did it without using this at all. If we go further with Rudin's book, after we've finished these proofs, we'll be able to use the square root of 2 because now we're going to be in real numbers. And then Rudin is going to be using square roots as much as he uses division in order to prove things. I think he thinks very numerically. It's really interesting that Landau did it without using arithmetic at all. We haven't really proven that Rudin's method won't work, but I think we've demonstrated a very strong possibility that Rudin's proof won't work. It's interesting that with Rudin's book, Rudin continues doing it this way. He continues with his arithmetical methods, and then especially if you're familiar with them, all the different tests for proving whether a sequence converges. It's all about comparing to sequences that we know where they go, and it's all very numerical. It's interesting that Landau did all of that without looking at the numbers at all, and it makes me wonder how far you could go using Landau's methods. Are Rudin's methods necessary at some point, or are they necessary ever? The bottom line is, it's very interesting that there's different ways of doing things. And in this situation, starting out trying to do it Ruden's way didn't even work. And we had to back way up and think of it a completely different way in order to get to the solution. So anyway, it's all very interesting. We're done with step 5 now, and next week we'll start on step 6, and then we're almost done with constructing the real numbers. Then I'm going to prove that the real numbers are unique, meaning that there is only one set that is an ordered field with the least upper bound property. And then we'll be done with real numbers and we'll move on to complex numbers. Thank you.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.